Okay, today's lab we're going to be looking at the effect that intermolecular forces have on evaporation. So I need to talk quickly about what evaporation is and what it means to say that evaporation is a cooling process. Now what we have over here in this picture is water. And remember, water has hydrogen bonding because oxygen and hydrogen have a very large difference in electronegativity. We get a very positive hydrogen, and that hydrogen is going to be attracted to the lone pair on a neighboring oxygen. Now this pink right here is the intermolecular force. Inter meaning between molecules. Now in order to have this liquid turn to a gas, we need to break this force. Now to evaporate something, you need to completely break that force. If we were only melting something, you need to sort of, I shouldn't say weaken it, you need to break that force as well, but you're not pushing those molecules super far apart. In this case, to go from a liquid where the particles are close together to where they're completely separated and no force at all pretty much holding them together, we're looking at the energy needed to break this. Now, evaporation, and depending on the substance, obviously this is water, we're going to be also looking at hexane, acetone, and ethyl alcohol or ethanol. And we're going to look at, well, how strong is this force between water molecules, or that force between hexane molecules, etc. Now, evaporation is an endothermic process. Endo means in, therm means heat. So it's a process that is absorbing heat from the surroundings. And I want to talk about examples of evaporation being cooling, which is what I have this list here. Your body cools itself through perspiration. And we know we do this, we sweat, and it's gross and it's disgusting, but if our body doesn't do that, we would overheat. And there are people that have a condition where they can't sweat. They have to be very, very careful about overheating, because what happens is you perspire, the perspiration goes on your skin, it pulls energy from your body to evaporate, causing your body to cool down because it's pulling energy from the body. Now, the reason I have Arizona versus Connecticut, we all live in Connecticut, and we've all experienced those disgusting Connecticut summers where it's August and it's 90 degrees and 90% humidity, and you feel like you're just sitting just in a pile of your own sweat because the sweat can't evaporate, and it feels so much hotter because the sweat can't evaporate. But if you go to something like Arizona, where the humidity is in single digits or even low double digits, as soon as you perspire, the water in your perspiration just evaporates and it feels cooler, which is why people will often say, well, it's 90 degrees, but it's a dry heat. Dry heat, it's still hot, but it definitely doesn't feel the same as when it's got that high humidity. I have a student I was teasing about being afraid of shots, but every time you get a shot, what do they do to your arm? They take that alcohol swab and they swab your arm, and your arm immediately feels cold. The reason it feels cold is because the alcohol immediately evaporates from your skin, pulling energy from your skin. Heat is leaving your body. It feels cold. Now, the reason I have a cat and a dog, cats, dogs, pigs, kangaroos, they don't perspire, so they have to cool their bodies some other way. Cats will lick their paws, kangaroos lick their paws, pigs will roll in the mud, and so they have water on their body. Dogs will pant, so the perspiration comes from their mouth, or the evaporation comes from their mouth, from the panting. So that's how they cool their bodies. This right here is just a general picture of like a very, very old ancient refrigerator. Basically, you take a pottery, you take like terracotta pottery, and you make an inner container and an outer chamber. And if you take this inner chamber, you surround it with sand, you put it in the outer pot, fill it with water. Now this pottery is permeable to water. So think like a brick. If you take a brick and you put it in water, you'll see the water kind of rise up the brick. So this outer chamber allows water to pass through it. And the evaporation, the slow evaporation of the water, causes the inside to cool. And you can get this down to probably 50 degrees, maybe even high 40s, just to the rate of evaporation. And so ancient cultures would use something like this to cool their substances. Now, what we're looking at in this lab is evaporation as an indirect way to measure the intermolecular force. So if we have strong intermolecular forces, we have strong forces holding these molecules together, it's going to take more energy for it to evaporate. More energy to evaporate means it's going to evaporate more slowly, and there's going to be a smaller temperature change in the liquid that we're monitoring. And you'll see what we mean when we go to do the procedure. Now remember, London dispersion, if something is completely nonpolar, that's all it has for intermolecular forces. That's the weakest of the intermolecular forces. If something is polar, if a molecule is polar, we have a permanent negative side and a permanent positive side. That's called the dipole-dipole force, and that's going to be in between. And then we have hydrogen bonding. And hydrogen bonding is what is present in water, which we talked about at the beginning of the video, where hydrogen has to be bonded to oxygen, nitrogen, or fluorine. And then we get that very positive hydrogen, which will be attracted to an electron pair on a neighboring molecule. All right, so we're at the procedure part now. And so what we're doing is I have a test tube filled with liquid, and this one is water. And in the test tube, I have a thermometer that has filter paper on it. You can see the filter paper. Now what we're going to do is we're going to pull the thermometer out of the liquid, and I'm going to rest it on the counter. When I rest it on the counter, I'm going to say go. The go is your 0 point. That is your initial temperature of the water. And it's the initial temperature of the water that's on the filter paper. You are then going to record the temperature every 30 seconds until I say stop. So we're going to look at the temperature drop until it stops changing, until the temperature goes up, or until a total of 8 minutes. Now, I'm not going to do the recording for you, so maybe have a stopwatch or have a clock, or you can look at the time stamp on the video. But every 30 seconds, you're going to take the temperature. All right, so I'm going to pull it out. Go. Okay, the temperature stayed about stable now for about a minute, so we can stop. All right, so the one we're going to do now is ethanol or ethyl alcohol. So I'm put this in. Go. we can stop. All right, so now we're going to be working with acetone. Now this is not smell-o-vision, so you don't get to smell it, but acetone is what is in nail polish remover. So if you've used nail polish remover and that distinctive smell, that's acetone. So I'm putting this in. Go. Okay, it's starting to go back up again, so we can stop. Okay, now we have hexane. I take my thermometer, put it in, get it on. Okay, go. Okay, it's starting to go back up, the temperature, so we can stop. Okay, for this part, we're looking at something called viscosity. Now, viscosity is a resistance to flow. Now, what we have is and they're labeled, we have ethanol, we have water, we have glycerin, and we have mineral oil. So we have 4 substances. And there's a little air bubble. And I'm going to flip it, and you're going to rank which one does the bubble move the fastest in, and which one does the bubble move the slowest in. If it moves the slowest, it's more viscous, and I will let you determine that if it's more viscous, if it has stronger or weaker intermolecular forces. If it moves quickly, it's not very viscous, it's not very resistant to flow. Now, I'm going to flip this, and let me try and do this here. I'm going to do it a couple times. okay? Because a couple of them are pretty close. Okay, flip it again. Right? Okay. Again. Do it one more time.